Yeah, I went to
70s.
juvie.
So let's go. Here we go. First thing is, we're on chapter 4, naming molecular and ionic compounds. So first thing is binary compounds. How many wheels in a bicycle?
2.
2. So how many elements in a binary compound?
2.
Could I have more than one of the element? Could I have more than one of each element?
Yes.
Yes, I could have like H2O. Yes, or
And
Al2O3. But the key point is there's only 2 types, right? I'm gonna.
No, please no.
We're good.
She was
Okay.
giving me binary compound examples.
Ah,
Yeah.
excellent. Okay.
Like NA.
So first thing is binary compounds.
I think you do.
Binary compounds end in
Ide.
just like Caesar.
Ice?
Ides of March.
There we go.
Oh my
Remember
god,
it.
good job, Jen.
Go, Jen.
Binary compounds end in ide. Anything else end in ide? Yes. Single negative ions. So if you saw something like this, if you saw this guy, what's it called? Fluorine. If you saw this guy, what's this guy called? Fluoride. What? Single negative ions, if they're alone like this, they end in ide. Now contrast that with this. Here's calcium. Calcium. And what's the positive ion called?
Calcium.
Calcium. It doesn't change its name. Positive ions, same name. Calcium, calcium. But the negative ions do what? Change to ide. And then when they hook up with a metal, they're going to keep their ide, and that's why binary compounds end in ide, because they hook up with a metal over here. And what kind of a compound?
Ionic.
Ionic is a metal plus what?
Non-metal.
A non-metal. So we have a metal plus a non-metal, we get an ionic compound. Versus the other type of compound, molecular or covalent. And what's the covalent compound?
Non-metal.
It's a non-metal plus what?
Non-metal.
Plus a non-metal. So guys, this is not rocket science, but you have to remember this. It's real simple. You look at a compound, all you have to do is look at the first element in the compound. First element in the compound. If it's a metal, the compound's. If the first element is a non-metal, the compound is covalent. It's that simple. So you can distinguish between ionic and covalent just like that. Look at the first element in each compound. Now, to understand this in the context of the periodic table, we're going to draw the periodic table up here. And then we're going to put this little boron right here, and then we have like 1, 2, 3, 4, 5, 6 columns over here, 2 columns over here. And then we get this little stair step. And we go, oh yeah, that's what I'm talking about. Okay. Now, this stair step is called what? They're called metalloids or non-metals. What does she use? Metalloids?
Yeah.
Okay. Note, metalloids count as non-metals. Note, metalloids count as non-metals. Note, metalloids count as non-metals. Now, everybody over here, all these guys in red, these guys are the non-metals, including what? Including the metalloids. Okay? Everybody else on the table, the blues, are what?
Metal.
Metals. So these guys are all metals. Now, if we take a red and if we take a blue and a red, and we put them together, what kind of compound do we get?
Purple.
All right, get a wise ass. Now, but what real kind of compound do we get? Ionic or covalent?
Ionic.
Ionic. Good. Right now, key point. There's 2 types of metals. There's 2 types of metals. There's the regular metals, and there are the trannies. You have to make a distinction in this chapter between the regular metals and the trannies. Regular metals only occur in 3 columns. Column 1, column 2, and column 3. Now, we know that all elements are neutral, but they have tendencies to form ions. First column forms what kind of ion?
Minus? So you add an electron, which makes them Negative.
No, they lose an
It's a
Lose an
electron.
electron.
It's plus
Metals
one.
are losers.
There we go. Metals are losers, guys.
So what was it, cation?
Yes, cations.
So good.
That's cations. Jen, that's going to haunt you all year. It's never going to go away.
Some people are trying to pay attention, Jen, so... Yikes.
So remember what we're saying. So first column, plus 1. How come? Because they do what?
They lose.
They lose an electron. Now the number of protons doesn't change. Number of protons doesn't change. If the number of electrons diminishes and the proton stays the same, the element is going to have a plus 1 ion charge. Everybody with me on that?
Yes.
Everybody in the second column wants to do what? Wants to lose
2.
and therefore they're going to become plus 2. And except for boron, which is kind of an exception, so leave it alone for now. Starting with aluminum, right here. In this column, they want to lose 3, so they're going to become plus 3. Now these are fixed charges. Everybody in the column has a plus 1. Everybody has a plus 2. Everybody below boron has a plus 3. There's a couple of other exceptions here, but that's the key point to keep in mind. Those are called what kind of metals? Regular metals. They're just regular guys. And they have fixed charges. Anybody in this column we know is about plus 1. Plus 2, plus 3, you can see it without any kind of special cheat sheet. And over here in the carbon column, for the carbon column we just say don't worry about it for now because it has its own chapter later on by itself. And then starting here with what? Nitrogen, oxygen, fluorine, and neon. What happens with the nonmetals? Do they want to gain or lose?
Gain.
Think about it. Do they want to gain or lose?
Gain.
Gain.
They want to gain. Now, if you gain electrons, you become positive or negative.
Negative.
So
Okay.
it turns out that nitrogen becomes negative 3, oxygen negative 2, fluorine minus 1, and the noble gases 0. So you don't need a cheat sheet for this, guys. All you have to do is visualize the periodic table or look at it in the room. And you can see right away, the first column, plus 1. Second column, plus 2. Third column, plus 3. Stop. And then what happens? Minus 3, minus 2, minus 1, none. So it's really easy to remember the fixed charges for the regular metals and the nonmetals. Now the trannies are a different story entirely. They're trannies, so we're not quite sure what their charge is. And it turns out their charge varies depending on who they're hooked up with for the evening. So, for example, the trannies can be plus 1, or plus 2, exactly, plus 3, plus 4, plus 5, plus 6. In other words, we don't know what they are. They're going to lose an electron, or 2, or 3, or 4, or 5, or 6. But you can't be sure what their charge is going to be because it varies. So far, so good? So we got the regular metals with fixed charges. We got the transition metals with variable charges. And we got the nonmetals. And we're going to put those guys together into various combinations. And we're going to name them according to the combinations we put them into. So, first naming is called type 1. And type 1 is just a regular metal plus a nonmetal. So, if we take a type 1, I think these typings are really stupid. This book is the only one that uses these types. They're not really necessary, except she probably expects you to know them, right? So, type 1 is a regular metal plus a nonmetal. So let's just take a simple one. Let's take sodium and hook it up with chlorine. Type 1, metal plus nonmetal. Then let's take another one, Mg, and hook it up with fluorine. And let's take a third one, Al, and hook it up with oxygen. Now, what's wrong with this picture so far? Can I just put the elements together and think I'm cool?
No.
What do you got to do for the ionic compounds? And how do we know it's ionic? Because it starts with a metal. What do we have to do with the ionic compounds to figure out what the combinations are going to be?
Flip, flop, and drop.
Flip, flop, and drop. Remember how we do that? And how to flip, flop, and drop is what? We take the charge and we put it up here, like plus 1 for Na,
Oh, yeah.
which happens to be like right here. And what's chlorine? What's charge on chlorine?
Minus 1.
Minus 1. So, do we have to flip-flop when the charges are the same, or do we just
No,
drop
you
them?
just drop them.
So there's the first one. Next one. Mg happens to be over here in the second column. So its charge is
Plus 2.
plus 2, and fluorine is way over here. It's minus 1. So what happens now?
You need 2 F's.
I need 2 F's. MgF2. Everybody with me?
Yep.
And it's still an ionic compound because it starts with a metal. Now what about this guy? What's aluminum? It's in the plus 3 column, so over here, and oxygen is in the minus 2, so it transfers 6 electrons to the oxygen, and the oxygen takes in 6 electrons, and you get Al2O3. Remember how we did this last week? This is just transfer of electrons. Do I need to break it down any more than that, or are you guys okay with the flip-flopping and dropping?
Okay.
Okay, remember what this really means is 2 aluminums with a +3 charge. Each of the 2 aluminums gives up 3 electrons for a total of 6. And 3 oxygens each want 2, and they grab 2, 2, and 2 for a total of 6. And that's how we get the quick Al2O3 combination. Okay, now let's name it. Naming is so simple. All you do is say the names. Sodium, positive ions, say their name, and then chlorine changes to chloride. What about this one? Magnesium, fluoride. What about this one?
Aluminum oxide.
Right, now we didn't use the subscripts in the names, did we? We just said the name of the compound without specifying the subscripts. Okay, so contrast that with this. Type 3. Turns out the type 3 is the opposite of ionic, and the opposite of ionic is, anybody remember?
Covalent.
Covalent. And covalent starts with a
Non-metal.
non-metal. So let's take this guy right here, and let's take this guy right here, and then we'll take this guy right here for fun. Oh, and this one too. Okay, so they're all covalent compounds. By the way, did I mention, I don't think I did, that hydrogen up here is kind of a joker in the deck? It hangs out with the metals, but it's really a non-metal. So hydrogen and the metalloids are all considered non-metals.
Are the metalloids both sides of the staircase?
Up and down, up and down, up and down, yes.
Okay.
There's only 6 of them, 1, 2, 3, 4, 5, 6, there's really 7. But your book somehow doesn't consider moron a metalloid.
Moron?
Yeah, it's a moron, the book is. So I'm leaving it out like that in case, I don't know how she's going to deal with it. You know, if she wants to call it a metalloid, fine. If she wants to follow the book and say it's not, then fine. Whatever she says, fine. Salute, say yes, ma'am. Go ahead. Question, Trevor? No, just exercising that wrist?
Yeah.
Our little tennis thing going on? Okay, so,
Period.
first one, let's see. Connor, what's the name for this guy?
7th period.
Carbon oxide.
Guys, everybody look. Is that right? Say it again.
Carbon oxide.
Ben, is he right?
Carbon
Oh,
dioxide.
sorry. Yeah.
Oh.
Carbon dioxide? How come not carbon oxide?
Because it's 2 non-metals.
It's 2 nonmetals, and so you got to say di. If you have a covalent compound, you've got to say di or
Try.
or
Tetra.
Tetra.
Or etc.
Penta.
penta, and got to put a Halloween hexon.
Wait, but it was like MgF2 and the one above.
Yeah.
So you say di?
No. These guys right here, it was just magnesium fluoride. So metals or ionic compounds never say di, or tri, or tetra, or pent, or hex. And, key point, everybody listen, they never let anybody else say di either. So over here, magnesium doesn't have a 2 here, but fluorine does. And magnesium, if fluorine wants to say difluoride, what does magnesium do? Slaps fluorine up and says, shut up. So you just can't say it. If you're in the presence of a metal, you can't say di, tri, or tetra. Metal just says, shut up. So, key point to remember. Now over here, this guy's going to be what? It's not going to be dialuminum trioxide. It's going to be aluminum oxide. You got it, Connor?
Yeah.
But down here, this is the contrast. With the nonmetals, with the covalent compounds, you've got to say di, or tri, or tetra, or pent, or hex. So, this guy is carbon dioxide. Next one, Ellie, name that tune.